Okay, so let's start talking about entropy. And entropy, what that is a measure of disorder, how disordered something is. So if you imagine that we have a bingo card, and what we're going to do is we're going to roll a dice, and if the dice comes up with that number, we're going to put a dot in that square. So I'll go ahead and number these 7, 8, 9, 10, 11, and 12. So we're going to roll the dice for this, and let's say we get a 1. And we want to know what is the probability that we're going to get, let's say, a 2, a 6, or a 5 versus getting something like 3, 4, 7, 8, 12, 11, 10, or 9. Well, if you look at this, it's probably more likely we're going to get something in like this orange versus getting something like in this pink. And that's because there's more orange than there is pink. And so there's a higher probability that when we roll the dice again, that we're going to get something like maybe like a 7. And then we roll the dice again, and then we get like maybe a 10. We would kind of expect this. And this kind of randomness where the numbers can be anywhere on this bingo card, we call that disorder, or this has a lot of disorder. We can also say that it has less order. Less order. We could say it's got more disorder, or we could say it has less order, like that. So let's look at this again, the same scenario where we have a bingo card again. And so we'll go ahead and number these 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. And so what we're going to do is we're going to roll a dice. And let's say we get a 1, right? So we roll the dice and we get a 1. And we roll the dice again, and let's say this time we get a 2. And then we roll the dice again and we get a 3. And then you roll it again and then you get a 4. Well, we're starting to see a pattern form when we roll these dices. And when we roll it again, we'll make this like 13, 14, 14, and 15. And then roll the dice again and we say, okay, we get a 13. We get a pattern here. We're starting to see these, it's always the top row. And so if you can predict where the next dot's going to go, we call that a lot of order. So we'll say this has lots of order. Okay? Or we could say it's got less disorder. Less disorder. It means the same thing. And so what entropy is a measure of disorder. And so if something's going to have a lot of disorder, like something over here, we're going to say the delta S for this is going to be some positive number. It's going to increase. The amount of disorder is going to increase if we have something like this. If we were to put another dot in here, the amount of disorder is going up. Whereas if something's over here, when we go to put that next dot in there, it's going to be a lot of order. So order is going to be increasing if every single time we keep putting the dots on this top row. We know exactly where this is going to go. Okay? And so this, we're going to say delta S is going to be a negative value, or it's going to decrease. And so to bring this back to chemistry, what this means is if you look at a solid, solids, they're very structured. The molecules are very structured in this like sort of pattern like this. And so if you look up maybe like online at molecular solids, they all got like the molecules are all like covalently bonded, and there's just like nice order to them. For the most part. Some molecules might have a little bit more order than others, but they're all pretty much kind of all lined up. Something that has a lot of disorder. When we talked about gases, and we said we had like a container and we had some gases in here, we said that the molecules are like going in like random places. They're all like bouncing off, and they can be like anywhere because they're like constantly moving around. And so we will say that gases over here have a lot of disorder. So maybe we'll put like gases over here. Well, these are like the gases because they're all in random spots. So let's put gas over there. Okay, so gases are like all over the place. And then this nice structured order, like this would be like your solid. And then the liquid would be kind of in the middle. So as you go this way, as you go from like a gas to a liquid to a solid like this, it means that the delta S for this going, you see, going like this is becoming more ordered. Delta S will be negative. Delta S is going to be negative. But as we go in this direction, as if we have a solid and that solid becomes a gas, delta S is increasing as you move along this this path here in the pink. And so let's try some example questions that I gave you in class that's going to look a little bit like mastering chemistry. And so let's see if we have some questions. Let's see, like this. Here we go. Okay, so what we have here is we have a solid, right? And then that's going to make a solid over here. So that doesn't do anything. It's like a solid makes a solid. The change wouldn't really be anything. But if you look over here, look, I've got a gas. I went from a solid over here, and now I've got a gas. And gases, we know, are very disordered. This is lots of disorder. Okay, so we got lots of disorder. So that's why for this one, the answer is delta S is going to increase. We're increasing the amount of disorder. So we put a positive delta S there. Okay, so what about this one? We got liquid going to a solid. Well, solid's got lots of order. It's got lots of order here, right? Because we get the solid there. And so we're going in the other direction. So it's going to be a negative. So if you want, you could put like solid, liquid, and then aqueous like this. And so here's where we're moving along. And you'll notice that as we go this way, I'm going to put a gas there instead. Should put a gas. As we got gas like that. As we go in this way, delta S is going to increase. Okay? And then as you go in the other direction, like this, delta S is going to decrease. And so we got liquid go to solid. We got liquid going to solid. So that's going to be, it decreases. All right. Let's try this one. This one's a little tricky now because you got gas here for both the reactants, and then what it's going to go to is another gas. And so when you have like all of the same phase, what you want to do is you want to count how many moles of gas do you have over here. And so I have 1 here, and then I have 3 here. I got 1 and 3. So I have 4 moles of a gas over there. And then that's going to go and make, I just got 2 over here. So I got 2 moles of a gas. So you go from 4 moles of gas. Gases are a lot of disorder. I have a lot of disorder, and now look, I don't have as much disorder. I've got more order over here. And so delta S will decrease, right? We're making more order. I went from lots of things going in crazy directions to fewer things going in crazy directions, okay? Let's try this one. I got a solid, and then I go over to aqueous. Well, solid, that has the most order, all right, of anything. A solid's got lots of order, a very structured pattern. And so if you look at this, a solid going to anything is going to increase the amount of entropy, right? So that's what that's going to look like. Okay. The other area that this kind of goes into in this mastering chemistry is it talks about the entropy of the surroundings. And so what I want to do is talk about a little bit about the surroundings. Okay. So we went over delta S of the system. Delta S of the system. You could think of that as the reaction. Okay. You want to, when you have delta S of the system, you want to think about what is the reaction doing. Okay. And that will tell you if it's going to be positive or negative. If you want to get an actual number for this, if you want delta S of the system and you want an actual number, what you're going to do is you're going to do the same equation that you use for delta H when we did products minus the reactants. And so what that equation looks like is this. It's going to be the sum. I'm going to have moles there, and then I'm going to have this delta S there. And this would be the products. Okay? And then you're going to subtract that from the sum of moles of this delta S of the reactants. Okay, so this is going to be an equation that you'll use if you want to get an actual number. And so we didn't go over any worksheets that were just like this, but what we did do is we did this. We did delta H for the reaction. It's going to equal sum of N times delta H formation, and we said this was going to be the products. And then we did something kind of like this, delta H, and we had something kind of like this, and this was reactants. Okay, so what we did was this, and this is the same equation. You're using the same concept, and we did a worksheet on this. And if you need a refresher on this part, I have that right here. So that's going to be something like this. So here's a good example. We have these two are going to be reactants. Reactants are always to the left, and then it's going to make products. Okay, those are always to the left of the side. Those are always going to be on the right side. The products are always on the right. And so you want to take the products, right, which would be, for this problem, it would be these two, this one and this one, and you're going to look at this table down here. Now, this table may not have all the numbers in there, but so you got to watch your phases too. See, I got H2O as a liquid, and I think this table kind of cut off where the H2O gas was, but you want to make sure that you're in the same phases over here. And so what you're going to do, because I got the answers right in here, is I think this one might be the NaCl, or let's see, or no, this one, sorry, this one will be NaCl over here, because you got products minus reactant, so the products will be over here. So this looks like it's going to be the NaCl, and that number is going to be right here. Okay, so NaCl, and see how I got one of these here? I'm going to do 1 times this. That's why there's only one of those. And then so what we're going to do is we're going to add these up. This must be the gas right here. This must be H2O as a gas. Okay, so we add up those numbers, and then we're going to subtract it from these over here. These right here are going to be the products, and these over here are going to be the reactants. And then you get this number. This number right here, this is delta H for this reaction. That's going to be useful later when we talk about delta S of the surroundings, because delta S of the surroundings, I'll go over this again later, but it's going to be this. Okay, that's what that's going to be. And so here's a way that you could find this delta H. Okay, now we did all this worksheet on this, so you should have, you know, some of these answers in there. But you know, if you don't, you can look at this and see, okay, I got, let's like look at B. I've got CO2, and see how I got 2 of these, and it's a product. That's why that 2 is right there, because let me put that in like pink right here. This 2 here is because of this 2 right there. Okay, so we got products, and then you got minus, and then you got reactants over there. Okay, so you can try some of these problems out, and see if you get these questions right. Okay, so that's all going to be this delta S of the system. So we went over delta S of the system, which was really just delta S of the reaction. Now what we're going to do is we're going to talk about delta S of the surroundings. So before we talk about that, let's talk about what happens for the system part. The system part, we said as we go from solid to liquid to gas, what happens is entropy goes up, right? So as we move along this, we said delta S is going to be some positive number. And so if that's going to be positive, think about why is that positive? It's because when you have a solid, all the molecules are perfectly lined up like this, right? So this would be my solid. As I move over into like the liquid phase over here, I have to add heat. We're going to add some heat. And what that heat does is, as you add heat, molecules start moving faster and faster, and they start moving around more. Well, think about your bingo card. If you have a bingo card like this, and we start lining up these dots like this, and then let's say on occasion I take a number and then I move it down here. I move it up here. I move, and it's like, you know, our structured pattern is not becoming so structured anymore, and it's because I'm kind of like moving these around, and that's kind of like what temperature does. Temperature is going to move these molecules around more, and so maybe we don't make it quite to a liquid just yet, because a liquid's like going to be like kind of like spaced out like this, but a solid, they start as a solid, and you add heat. Maybe one of these jumps up there, and then one of these jumps up there. It's kind of like you had a bingo card, and then an earthquake happens and messes up all your chips. Well, that earthquake is kind of like what you do when you add this heat. It's messing up this kind of structure. Eventually, it will be so messed up. These molecules will be so scrambled that we'll just call it a liquid. But basically, my point is that as you add heat, as you increase heat, delta S goes up. We're increasing more disorder. And so keep that in mind when we work with this delta S of the surroundings. As you add heat, it becomes more disordered. If it becomes more disordered, delta S, like we said, will be positive. Okay? So that's what we have for that. And so let's go back to this idea of calorimeters. We talked about calorimeters a few weeks ago. And so a calorimeter, if you have a container like this, and here's the reaction, right? Here's the reaction, which would really just be the system, right? System and the reaction are kind of the same type of thing. Here it is here. And then what's going to happen is heat is going to flow, let's say, from the reaction to the surroundings. Okay? Well, if this happens, the system is making the surroundings get hot, right? This gets hot. The temperature, it goes up over here. And if the temperature over here goes up, so does the delta S of the surroundings, right? So this is getting more hot. But let's think about what is happening in this reaction. This reaction is giving off heat. And what do we know about heat? That tells us a delta H value. If delta H is going to be a negative value, that means the reaction, I'll put the reaction, is going to give off heat, right? The reaction is going to release heat, and it releases heat to the surroundings. And if the surroundings gets hot, molecules start going faster and faster, and you increase the amount of disorder of the surroundings. And so the equation for that, the equation for delta S of the surroundings is going to be negative delta H over the temperature. Okay, and the temperature, where you have to watch out, it must be in Kelvin. So I'll put must be in Kelvin. Okay, temperature's got to be in Kelvin. And so let's say, like the reverse of this. Let's say we have a calorimeter like this, and we have the reaction right here, and which would also be called the system. And then what we have is heat is going to flow away from the surroundings. Right, here are the surroundings, and it's going into the system. Well, the reaction is requiring energy for this thing to happen. And so what you can think of is this. If we have H2O, and we'll say that's going to be, an example, like a liquid, and then we have this going to a gas. I'll just make up this example right here. Let's say you got a liquid going to a gas. If the way you're going to figure out what the sign is for delta H, because delta H will have some value, think about where would heat go in this problem. Would the heat go over here? Would you put heat here? Or would you put heat over here? Where's the heat going to eventually go? And so if you have like a pot of water right here, do you add heat to the water and then you get this? Or do you have your pot of water here, and then it somehow makes a gas, and then you get some heat? Well, no. What you probably know is you take your pot of water, you add to that heat, and then you get this gas over here. So if you're going to add heat, it means that delta H will be a positive. Delta H is requiring amount of heat. So this is going to be the heat that's going to be required to do this. And so if this reaction right here, we'll say this reaction right in here, if this reaction requires heat, Where's it going to get that heat from? There's only the surroundings to get that heat in. So the surroundings is giving heat over here. And so delta H for the reaction, delta H would be a positive number for this. And heat is leaving, which means this over here, the surroundings, is going to get cold. All right, because you had a lot of molecules going real fast, but you had to use some energy to put it over here. So the surroundings gets colder. So delta H for this would be positive, like we said. And so what would happen to the surroundings? The surroundings would become more ordered. You're going to get more order over here. Well, let's go back to this equation. Let me erase some of this, and we'll talk about this equation. The equation says, it says this right here. Let me read. I'll put it over there. So it says this. Delta S of the surroundings is going to equal negative delta H. Well, delta H was going to be a positive. We'll just make that like a positive, like 5. Okay? We'll just make up a number. Say it's positive 5. And then divide by the temperature. Now, we'll make the temperature like 1 Kelvin. You know, you'll probably never see this, but we'll just make it 1 Kelvin to keep the math simple. That's going to be divided by 1. So delta S of the surroundings is going to be negative 5. Well, think about it. Does that make sense? The surroundings gets cold because the reactions require energy, and so we're getting more order for the surroundings. And look, it's a negative number here. That's what you would expect, because a positive number here, a positive delta S of the surroundings, means you're becoming more disordered, like over here. This is making more disorder. So a very common mistake that I see a lot of students make is they don't take into account that negative. If delta H was negative, you have delta H equals negative 5, kilojoules per mole, then this would be what? Let me erase some of this. Erase this over here. Let's just say, let's use this example. Let's say delta H over here is going to be negative 5. Okay, we'll use this equation right here. Okay, so negative 5, and let's say it's going to be 1 Kelvin again. We'll put 1 down. Well, this is going to be delta S of the surroundings. It equals that. If you got negative here, that's going to turn that into a positive 5. So this would be plus 5. So the amount of disorder would go up for the surroundings, and that's exactly what we see here. The reaction is giving heat over here to the surroundings. The molecules are going faster and faster. They're going crazy because you've added heat to it, and so the amount of disorder for that goes up. Okay. And you might be thinking, well, doesn't the reaction, if this is going to become more disordered, or does this become more ordered? And it's kind of tricky, because if you look in your notes, the highest priority that you want to look at is going to be the phase changes. That's going to be the biggest clue. Not so much if heat's going in or out. So for the reaction, you want to follow this. Okay, you want to follow that, and then for the surroundings, you want to follow heat. So let's write that down. For delta S, anytime you're asked about delta S, what you want to do, or let me see, delta S of the system. If it's delta S of the system, what you want to do is you want to look for a phase change. You want to look for a change in the phase. Okay, you want to do that, and that will tell you the sign. Okay, that's just going to tell you the sign. Another way delta S is you can do products minus reactants, and that's going to give you an actual number. Okay, so if you want an actual number, you can do products minus reactants, or sometimes they might even just give it to you. They might see something like this, where it says delta S, and sometimes they put a little circle right here. All this circle right there means is standard conditions. These are standard conditions, which means it's going to be 298 K. Okay. That's what you're going to use for standard conditions. Okay. And so you have that. Okay. Let's talk about delta S of the universe, or delta S total. Okay. So delta S total. Well, wait. Okay. So yeah, delta S total. I use universe, they use total, they mean the same thing. Okay? This has got to be greater than 0. It basically has to be a positive number if the reaction is spontaneous. So let's write that down. If the reaction is spontaneous, and we talked about spontaneous when we talked about delta G. So if the reaction is spontaneous, delta S of the universe, or delta S total, has got to be some positive number, okay? Because all, let me write this down, all reactions that are spontaneous increase the disorder of the universe, or we'll just say total, okay? Of the total entropy. Okay, that's what they do. Okay, so the delta S total, what that is, delta S total, it's going to equal delta S of the system plus delta S of the surroundings. Okay, so if you want to get a number here, you can do products minus reactants, like I showed you a second ago. And to get the number over here, what you can do is delta S of the surroundings. You're just going to follow the heat. You'll do negative delta H divided by temperature. The common mistake, what I see students make over and over and over again, is watching the sign. So let me put that down. I'll put beware over here. Beware. And I'll put the most common mistakes that I see. The first common mistake is I see the units. Okay, I see students mess up the units. Sometimes they'll give, because when they work with this equation right here, when you work with it, oftentimes, not always, but oftentimes this will be in kilojoules. A kilojoule and a joule, they're the same thing. It's just a different, it's like meters and kilometers. You know, it's like you use Celsius or Fahrenheit. They mean the same thing. It's just different conversion. So this delta H is going to be kilojoules. And this over here is going to be most likely joules. So watch your units when you do these calculations. The second area that I see students make is you have to use Kelvin. They didn't convert their kelvins right. And so the Kelvin, you have to do that here. Okay, that temperature has got to be in Kelvin. See, the third thing that I see students make is the negative sign. So we'll do negative sign. And what I mean by that is this negative sign right here. They forget to flip this, delta H, because this delta H right here, what this delta H is, it's of the reaction. Okay, that's for the reaction, that's for the surroundings. Over here, the system, that's kind of part of the reaction too. Okay, this is the reaction, and then this right here is the reaction, but this right here is the surroundings. And so the equation for the surroundings, you need to know delta H of the system, or delta H of the reaction. And so let's see. I think the other thing on this Mastering Chemistry, talked a little bit about delta G. So let's go over this delta G concept and what spontaneous and non-spontaneous is for that. And so let's see. We have delta G here. Okay, delta G is delta H minus T delta S. Again, this has got to be in Kelvin. And also watch your units. Units here and units here. Like I said, this is usually kilojoules, and that's usually going to be joules. And delta G, I see a lot of times they'll have it in kilojoules, but not always. So watch your units for all these stuff. Okay. Okay, so we got all that. And what delta G will tell you if the reaction is going to be spontaneous or not. So if delta G is negative, it means the reaction is spontaneous. If delta G is going to be a positive, it means the reaction is going to be non-spontaneous. If delta G is going to be 0, it means you're going to be at equilibrium. Okay? So that's all delta G stuff. For delta H, if it's going to be a negative, it means that heat is released. So I'll put heat released over here. If delta H is going to be a positive, I'm going to say heat's going to be required. Or sometimes Mastering Chemistry might say absorbed. Absorbed and required, same thing. All right? And then we already talked about delta S a little while ago. So let's say, well, another thing, that delta H over here, that's negative, Sometimes they'll say exothermic. Exo, you could think of, exo means leaving, is exiting, and thermic means heat. So we got that. And then you got endo, it's going in, endothermic. Okay, so we got heat exiting, heat leaving. All that means is it just tells you the sign for this delta H over there. Okay, and so let's say we have something like this. Delta G equals, let's say delta H, we're going to make that negative. So this is an exothermic process, so delta H will be a negative. And then the temperature, when you use Kelvin, the temperature will always be, when you use temperature is always going to be in Kelvin. Okay, so Kelvin has, for 0, it's an asymptote. So like if you were to plot temperatures on a graph like this, an asymptote is basically going to be where the point where it doesn't cross. So the temperature in Kelvin scale is kind of like this. It kind of like jumps. 0 is like the, you can't ever get there. It's kind of like that. And so what we'll do is say delta H is negative, and then we'll say, okay, let's do minus, temperature is going to be positive, so we can, that's going to be fine. And then let's say delta S, we're going to say this increases the amount of disorder. So we'll make that positive. So what this is saying right here, let me get that, I got pink. Let's say what this is saying right here is that this is going to be an exothermic, because delta H is going to be a negative, and then this minus sign there is that minus sign there, and then look, this delta S right here, that's going to be a positive. So that's telling you that this is going to make more disorder. So if they tell you on Mastering Chemistry, the question has exothermic, it's making more disorder, what does that tell you about this delta G over here? Well, if you solve this out, let's see, delta G is going to be, I got a minus, and then a negative, and then I got a minus, and then I got a plus. So what I can do is add the opposite like this. This delta G has to be negative. So what this tells you is that this must have a negative delta G. And what that tells you is if you have an exothermic process that creates more disorder, it will always be spontaneous. Okay? Reactions are either thermodynamically controlled or kinetically controlled. Right now we're talking about the thermodynamically controlled reactions. Those are going to always be spontaneous if the reaction is exothermic and it creates more disorder. Okay? And so let's say we have a reaction like this. Let me erase all this. Let's start over. Okay, so let's say, when we put this delta G back up here, delta G equals delta H minus T delta S. Well, let's say the reaction is going to be exothermic. Okay, exothermic. So what does that mean? That means delta H equals negative. And then let's say that we want to say this is going to be non-spontaneous. Non-spontaneous. Well, what does that mean? That means if it's non-spontaneous, that tells you delta G is going to be positive, right? Delta G is positive. It's non-spontaneous. Does not. And spontaneous and non-spontaneous. Spontaneous means the reaction happens all by itself. Like if I have my pen up here, here's my pen, whatever, and then I drop my pen on the floor, that's a delta G equals negative. That is a spontaneous process. It happens all by itself. We don't do anything to make that happen. It will just happen. Okay. And so let's say we have like an exothermic. All right, exothermic, delta H is negative, not spontaneous, delta G is positive. Let's see what that is. So we got positive here equals delta H is going to be a negative, and then I got minus the temperature is always going to be positive. So what does this have to be? Let's see, positive delta G, I got a negative and then a minus. So what does this have to be in order to make this thing? We want to make this thing in here be positive, so it can match that right there. Okay. Well, you're going to have to get that. If you put a negative in here, you can do this. You can say plus a positive. Then, if the temperature is very high, like so, we have a high temperature in here. Well, what that is, if this temperature is very high, this is going to be more than this, right? If this number is very high, it's going to cause this one to be the greater one, and it will outweigh that one. And so at a high temperature, this would be non-spontaneous. So let's see what that means. That's going to say what you want is this to be something kind of like this. You want to have negative here. That way you can do plus a positive. So you want this part in here, right, to have that negative sign. Okay, so you could say delta S like this, and then you'll have 0 over here. And so you want this to be a negative, so this would be something kind of like this. Okay, let's talk a little bit more about this concept of equilibrium. Okay, so when we talked about this like phase diagram, where we had a solid, and then remember this was like this right here was this part in pink. This was Q equals MC delta T, right? And then you had this right here. This was Q equals delta H times N, like this. And then what we did was we say in temperature kind of goes up like this, and then it goes flat like this, and then it went up, back up like this. And we said, okay, this was going to be the solid, right? That's a solid. And this was the liquid, and this was the gas. And over on this axis, this was the temperature, and this was the amount of heat. A solid to a liquid like this, that's going to be melting. I'm melting, like if I have like ice as a solid, and I go to a liquid like this, it's going to be melting. So if I go from this to this, if I go from a liquid to a solid, that's going to be freezing. Okay, so that's going to be freezing. And so if you look at that, that happens at the same temperature. The temperature is the same. So you can have solid go to a liquid and liquid go to a solid at the same temperature. These right here, I'll put that like this. These happen at the same temperature, like those two processes. So when you have something like that, where you have a solid go to a liquid and a liquid go to a solid, delta G is going to be 0 because you're at equilibrium. This is what equilibrium is. Okay. Spontaneous would be if it was solid and it was going to a liquid and then it doesn't go back. Like it's just one direction. Okay. And so that'll be delta G would be negative for that. But for at this temperature, right? That temperature, delta G is going to be 0. Okay, so I think I gave you a worksheet on something very kind of similar to that. And so that would help you do mastering chemistry. There's a question mastering chemistry just like it. So let's look at that. And so here's the worksheet that I gave you. And it says in here, well, I'll let you try this out, but so I got temperature here, I got delta H there. I'm trying to find this delta G, and I also have this delta S over here. First thing I do is check my units. Kilojoules there, so that's matched up, that's fine. That's Kelvin there, so you're okay. What you want to do for this is this this equation, and that's pretty straightforward. Where it gets a little tricky is this one right here, because this one you have delta S is positive, and this right here, the vaporization, vaporize, that's going to be a phase transition, and phase transitions are going to be a delta H value, and so this would be 31 kilojoules. This is in joules, so you got to watch your units there. So that's 31, and then delta S is going to be, what's that, 0.093, because I'll have to convert that. And so you want to find out what temperature, because the temperature, because this one's positive and that one's positive, Remember, if you look at your worksheet, the temperature is undetermined for this. It's undetermined. And the reason why it's undetermined is because these two will kind of clash. So let's see. We got like delta G equals delta H minus T delta S. So let's see. What would delta G be if delta H was a positive like it is here? And then we got positive, and then you got minus the temperature, and then you got, which was always, temperature is always positive, but it can be high or low. And then you got a positive here. Well, if you got positive minus another positive, well, if you want to do this, plus a negative right there, if this one's higher at high temperatures, this number is going to be large, right? If this temperature here is very large, it's going to make this number very large. And if this number is very large, this would have to be a negative. If the temperature is very low, it will make this number very small. If that's small, then this one's going to kind of win out when you go to add them up. And then this number here would have to be positive. So for this case where you have positive and positive, the reason why it's undetermined is because you don't know what the temperature is going to be, or the temperature kind of can flip on you. So it can be either spontaneous or sometimes non-spontaneous. And so the way I approach this problem, let me erase all this. The way I approach this problem like this, number 3, is I did this. We took my equation, delta G equals delta H minus T delta S, and I set delta G to 0. Okay, this is kind of combines a little bit of concepts that you did in the Mastering Chemistry. We set delta G to 0 at the boiling point. If the boiling point, okay, that's when you set that to 0 because you're at equilibrium. But we got that. Okay, so let's see, equals delta H is going to be 31, so we'll put 31 down, and then minus temperature. Temperature we don't know, so I'll put T there, and so delta S is going to be 0.093. So if you solve this at this temperature, I think the temperature is going to be like 333 is what we got. If you get that, if the temperature is 333, that's going to be right at the point where you're at equilibrium. Where, like, if you rank your temperatures on the scale, here's we'll put like temperature over here. We'll say like 333, and that's going to be Kelvin. Remember, that's going to be Kelvin. So if they want Celsius in Mastering Chemistry, you got to know how to convert that. You got to know that. Kelvin equals your degree Celsius plus 273. Okay, so that's how you convert from Celsius to Kelvin. But basically, this right here is going to be this 333, and so this will, can switch on you depending on if it's going to be higher or lower. Okay, so that's how you would do those questions. Okay, so if you have any other questions, you can come see me after school, and I can go over some of this stuff with you.